we've looked at two different ways that compounds can form. Rather, not form, but two identities they can have. We looked at metallic bonding, which was the sea of electrons that hold a metal sample together. Your copper penny, it's really zinc, but your penny is held together by lots of zinc atoms, all joined together metallically. We spent the bulk of last unit looking at ionic compounds. If we remember, ionic compounds were most generally dictated by a positive bonding with a negative, a cation with an anion, which in most cases could have been looked at as one item from the left of the zigzag bonding with an item to the right of the zigzag. And that was ionic. Now, keeping that definition in mind is important because but there's quite a few moments in this last unit of the semester that I'll ask you comparison questions. So remember some of your ionic basics. It was a plus bonding with a minus. It was a fragile crystal, a very weak bond, and all the other characteristics that we went over. This last unit will be different. We're not going to look at ionic. We're going to look at a different type of bond. It's called covalent. And this will probably be the most important thing I say today. To be covalent, the compound will be made up of two nonmetals. Those of y'all that are smart are drawing everything I draw anyway. To say it again, in order for a compound to be covalent, the two parts, it's going to be binary, just meaning two things joined together. The two parts, both of them, will basically come from the right of the zigzag. Two nonmetals bonded together. And this forms a very different type of compound. The first thing we're going to talk about is just the characteristics of these guys. But before we do so, somebody name two elements that will form a covalent compound. Oxygen and nitrogen. All right, I wrote that backwards. It'd actually be nitrogen and oxygen. But, yeah, that would be covalent because both of them are to the right of the zigzag. If you're wondering how I know nitrogen would come first when they bond together, it's like reading a book across the periodic table. Since nitrogen is to the left of oxygen on the PT, he would be to the left of oxygen here. Somebody name another compound that would be covalent. Sulfur and okay, does argon form a compound? Don't use the noble gases. They don't form compounds, all right, in this class at least, but generally they don't. Fluorine, yeah. Look at what they're doing. All they're doing is finding two elements that exist on the right of the zigzag, two nonmetals. The moment you grab something from this side, it's going to be ionic if you bond it with something from that side. Take a look at your new cheat sheet. It says a covalent compound forms when two nonmetals bond together. You knew where the nonmetals lived anyway prior to this unit. It says atoms are more stable when they are bonded into compounds. That sentence was word for word on your last cheat sheet. That's still true. The whole reason that two of these items are going to bond together is going to be to increase their stability. Everything wants to have the octet. But here's where things get different. In our ionic, electrons were donated. If you remember, whenever sodium, which had a Lewis structure that looked like that, bonded with chlorine, which had a Lewis structure that looked like this, there was a donation. Now this is ionic again, all right? This is review. All right, there was a donation of that electron to that spot. He actually gave it away. And then the resulting charge brought them together. Opposites attract, but that electrical attraction was very weak. Covalent is different. Instead of using the word donate, covalent uses the word share. Covalent shares electrons. And when you share electrons, as we'll see quite a bit in some pictures we'll draw tomorrow, the bonds are strong. It's very difficult to tear apart a covalent compound. Remember, the ionic guys are kind of like the magnets. If I walk by my refrigerator, I can just go like that to the magnets and they all fly off. But if they were covalent magnets, which now I'm totally making stuff up, I wouldn't be able to break that bond. Because listen again, sharing electrons instead of donating them builds a very strong bond. Super glue this time. But what's interesting is there's different ways that you can share. And here's where some vocab will start hitting you. Water looks like that. All right, it's two H's and an O. Water is covalent because hydrogen and oxygen are both nonmetals. There's a little bit of review for you. Remember, there's one nonmetal that lives to the left of the zigzag. Remember that rebel up there? Hydrogen? All right, so keep that in mind. All right, remember, by definition, covalent is two nonmetals bonding together. Hydrogen is the one nonmetal that lives to the left of the zigzag. So if I put H's and O's together, both nonmetals, it forms a covalent compound. We call that a molecule, all right? But the way that these electrons here are shared, I drew lines. I shouldn't have done that. You haven't seen that yet. But the way these electrons are shared can be even or uneven. For example, let's say that I had a pizza. And I brought the pizza in. And Rose over there was like, man, I'm starving. I'd love some pizza. So I cut the pizza right down the middle and I gave him half of it. Did I share the pizza? I shared it with him. Did I share it evenly? Yeah, I shared it right down the middle. Now, let's rewind. And I come in with the pizza. Again, Brian's like, dude, missed lunch. And I give him one slice. Did I share the pizza? I did. Did I share it evenly? No, this time I kept more of it for myself. Both of the examples are forms of sharing, but they were different types of sharing. Look at your cheat sheet. You'll see some vocab. It says a polar covalent bond is when electrons are shared unevenly. That would be when I give him just the one slice of pizza. A non-polar covalent bond is going to be when everything is evenly shared. I don't have a good way to show it to you yet. I'll do it in lab on Friday. But in this water molecule that you see here, hydrogen is sharing electrons with oxygen, forming a strong molecule. All right, covalent bonds are molecules, as your cheat sheet says, forming a strong molecule. However, the oxygen is actually hogging more of the electrons. This is a polar covalent bond because even though they're sharing these, the oxygen's actually pulling on those electrons harder than the hydrogen is. But there's other types of covalent compounds where the electrons are shared completely evenly, which would be described as nonpolar. So there's some vocab to get wrapped around your head. By the way, if you don't study those terms, you will guess them backwards. Nonpolar makes it sound like uneven sharing if you just start looking at the prefix non and stuff like that. So learn the vocab monkey grapefruit so that you know which vocab is uneven and which is even sharing. Now, I've said it a couple times. If you identify a compound as being covalent, then it's called a molecule. A word you heard before entering this class, but I've never used that word before. So, just as a quick little snapshot for your eyes, ionics formed weak crystals. That's review from before Thanksgiving. The new thing, yes, you're writing. Yeah, you're writing. Good job. The new thing is that covalents form strong molecules. This would be a great thing to just always carry around in your brain because you could probably apply this to a bunch of different questions. You could even add the definitions and say ionic is a positive bonding with a negative, which a lot of times can be said as a metal bonding to a nonmetal, whereas my covalents are going to be nonmetals bonding to nonmetals. All right, so again, review, but a snapshot of fantastic information to just have on your brain the next 2 weeks. But of course, we are focusing here on these molecules. And we have a special type of molecule I want to draw your attention to. Look at your cheat sheet where it says diatomic molecules. There's 7 elements on the periodic table that cannot exist by themselves. What that means is if you come across one of these 7 elements and they're not bonded to a different element, then they're going to be bonded to a copy of themselves. For example, what are you breathing right now? You're breathing oxygen, all right? It's just oxygen. It's not carbon dioxide. It's not oxygen bonded with a different element. It's oxygen that you're breathing in. But oxygen is one of my 7 diatomic molecules. And listen to the explanation again. The diatomic molecules are elements that cannot be by themselves. So you're actually not breathing in O. You're breathing in O2 because oxygen's on your list of 7. If oxygen is not bonded to a different element, then he's going to bond to a copy of himself. All of the oxygen you're breathing in is O2 because oxygen's diatomic and behaves this way. I want you to put your finger on nitrogen. Put your finger on nitrogen. While your finger is on nitrogen, I want you to run it over to fluorine while touching the paper. And then from fluorine, I want you to run your finger down to iodine and leave it there. Now take a finger from your other hand and put it on hydrogen. You've touched all 7 diatomic molecules. You can either memorize them or remember that little tetra shape plus hydrogen I just showed you. The diatomic molecules are nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. These are the 7 elements that act like this. Questions will often come like this. Only one of these is written correctly. Which one? Only carbon's is written correctly. Here's how they came with that. All right, carbon here has no subscript. Carbon is not diatomic, so he can exist by himself. Sulfur has a 2 written there, but sulfur is not diatomic. Sulfur can exist like that. Chlorine is diatomic. He's one of the 7 elements that's in that shape. So he should look like this because chlorine can't exist by himself. Another way that students memorize the 7 diatomic molecules is by an acronym called Brinkelhoff. I don't really teach Brinkelhoff, but if you put all 7 of their symbols together, you can make it spell Brinkelhoff. So some of y'all are looking at me funny right now. Figure it out, move the letters around. But if you like Brinkelhoff, whatever. You need to have the 7 diatomic molecules memorized. Any questions so far about covalent properties? We have to be able to name covalent molecules. This is nomenclature like the ionics. But when we started naming ionics, writing the formulas and stuff, there was a ton of rules. There was you crisscross the oxidation states unless they're the same number. But if you crisscross one to a polyatomic that's bigger than 1, you need parentheses. And if you run into a Roman numeral, you need to know that that represents a positive charge of a transition metal. Remember all that fun stuff? It was fun. Covalent nomenclature is much easier. There's not a long list of rules. Instead, there's just a short list of prefixes. A week from today, you need to be able to walk into my room and say mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And if you can do that, you're going to do really good on 30% of the questions on that test. Super quiz, whatever. There's that list I just spat out. Some of those prefixes are very common to you, actually. If I said tri, you could think of tricycle, has 3 wheels. All right? Or if I say octagon, you know that an octagon has 8 sides. So start using your word association immediately, but you need to have the prefixes 1 through 10 memorized for covalent nomenclature. So start working on it now. Let's take a look at what we're going to be doing here. Write it down. You're writing down everything. I'm writing down. Yay! Is this a covalent compound? Don't just shake your head or nod your head. Think about it. It's easy to know, but think about it before you answer. Is this covalent? It is. How do you know? Because they're both nonmetals. Nitrogen and fluorine are both on the right of the zigzag. It's covalent, which means we're not going to crisscross numbers or do anything. We're not going to use ionic rules. We're going to use new rules. Here's what they are. Follow along. First thing we want to do is name both elements. N is nitrogen. And F is fluorine, but we never, what do we always end the second, how do we end the second word? Ide. All right, remember that second word will end in ide, so fluoride. All right, so N is nitrogen, F is fluoride, and here's where the fun comes in. We go back and we look at the numbers that each have, and based off their own number, you give them a prefix. There's no crisscross, don't crisscross. All right, how many nitrogens are there? There's 2. What's the prefix for 2? Di. All right, it's what you want a nitrogen that you don't like to do. Die nitrogen, because you're going to kill him. Okay. The 2 is dinitrogen. How many fluorines are there? There's 1. What's the prefix for 1? Mono. You should just be reading it straight off the page. This is dinitrogen monofluoride. Yes, this is the unit where the names get very, very weird. But that's it. There's no other rules. There's one little rule, I'll throw it in a second. But this is really almost all of them. That says S807. Hey, is that covalent? It is covalent because both elements come from the right-hand side of the zigzag. They're both nonmetals. What is S? Sulfur. What is O? Oxide. It's oxygen, but the second word should end in IDE. Sulfur oxide. How many sulfurs are there? There's 8 sulfurs. I want that prefix to go in front of sulfur, which is going to be, it's octa. Octasulfur. How many oxygens are there? 7. What's the prefix for 7? Hepta. Octasulfur heptaoxide. CO3. Now, I told you there was one teeny tiny rule, so don't name this by yourself because you'll name it wrong. What is C? Carbon. What is O? Oxide. And here's the one rule that there is. We just never put mono in front of the first word. If there's only one of the first word, then you just don't give it a prefix. Now, mono is still good to use. Look, 2 examples earlier. We used mono in front of the second word. All right? But again, the rule is very simple. Never put mono in front of the first word. So this is going to be what? What's the final answer? Carbon trioxide. All right, and of course, CO2 is carbon dioxide, and CO is carbon monoxide. All of them poisonous. All 3 of those compounds are poison. Carbon dioxide. Where's carbon dioxide? What's the one of the biggest sources of carbon dioxide? What? Do you say chows? No, that's funny. That's methane. That's CH4 that you're thinking of. But carbon dioxide. Where does most of it come from? Us. Yes, it's what we're breathing out. You're breathing out a very poisonous gas. Did you know that? But plants love it. And carbon monoxide, all right, a big part of awful stuff that your car spits out and cigarettes and stuff like that. Let me give you a couple of these to try. See if you can name all 3 of those compounds. Let's see how you did. First off, I know that they're all covalent. I know you're not checking, but you need to. But they're all covalent because nonmetal, 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 they're all to the right of the zigzag. So, P is phosphorus. I is iodide, if it ends in IDE. 5 is penta. 10 is deca. Somebody say it, 'cause it's fun to say. It's hard to say. Pentaphosphorus, decaiodide. B is boron. Cl is chloride, ending in IDE. There's one boron, but we never put mono in front of the first word, so just leave it as boron. And there's hexachlorides. Br is bromine. Se is selenium, but I'm going to call him selenide. There's 9 bromines, which is nona. And there's 1 selenium, which is mono. Nonabromine monoselenide. How'd you do? You need to be able to go the other direction. Which is honestly just as easy. Let's take a look at it. If I give you the words, you need to be able to write the formula, but there's no crisscrossing or charge checking or any of that. If you know your prefixes, you're good to go. Write this down as we go the other way. Tetracarbon tetrasulfide. Again, this is very simple. Look at this word right there. Do you see the element? What element's in that word? Carbon. Carbon. Look at this word, tetrasulfide. What element's in that word? Sulfide, which is really sulfur ending in IDE. How many carbons are there? 4. All right. You don't have to have them memorized yet. Look at your list. Tetra is 4. How many sulfurs are there? Yeah, 4. They both had tetra. C4S4. Tetracarbon tetrasulfide. Identify the elements and then assign them numbers. Arsenic pentabromide. What element do you see in the first word? Arsenic, which is AS. Pentabromide. What element is in that word? Bromide, which is bromine. There is no crisscross. Be careful. Your brain will get all fouled up and say, well, doesn't the penta cross over to arsenic? Not in covalent. How many arsenics are there? There's 1. There is no prefix, which means there would have been mono, but we don't put mono, so no subscript. How many bromines are there? ASBR5. You try a couple. See if you can write down the formula for those 3 compounds. I'm actually going to add a bonus problem because I'm in a good mood. See if you can name all 4 of those. Let's see how you did. Silicon is Si. Monoiodide, I see iodide, which is iodine. There's no prefix in front of silicon, so I'm going to give him a 1. There's mono in front of iodine, so I'm going to give him a 1. We never show 1s as subscripts. Octacarbon, I see carbon. Diphosphide, I see phosphide, which is phosphorus. Octa, 8 carbons. Di, 2 phosphorus. Trichlorine, I see chlorine. Pentasulfide, sulfide is sulfur. Tri is 3. Penta is 5. Anybody get different answers for those? What'd you name him? He said trimagnesium dinitride. Anybody else? That's wrong. But you're not the only one to do it. This guy right here is why my final exam is really hard. Because one of the options will be trimagnesium dinitride. And based off today's lesson, that looks right, except magnesium lives on this side and nitrogen lives on that side. This is an ionic compound. You cannot apply covalent prefixes to an ionic compound. The only right way to name him is magnesium nitride. Magnesium nitride is the only right answer. I'll write it down. I see some of y'all want to. Magnesium nitride. Why does his formula look like that? Well, because magnesium is Mg, nitride is N, magnesium has an oxidation state of 2, nitrogen has an oxidation state of 3, they're different, so we crisscross, and it forms this. It's not going to bother you next Tuesday because I'm not going to mix up ionic and covalent, but my final exam will. And if you don't take the first step of saying, is this ionic or is this covalent, which is real simple. If they come from different sides of the line, then no prefixes. If they both come from the right, monoditride, tetra, blah, blah, blah.